Welcome back to the Natural Hogarithm. Let's talk about parametric integration. Now, many curves can be described by functions. We could have y equals x squared or y equals e to the x, but other curves are harder to define. Instead, we need to let x and y be functions of a separate variable, something like t or theta. This parameter is really up to us. However, from that, we can describe our curve not as a single function, but as a set of parametric equations. Now, the two questions I want to answer today are A, can we still integrate parametric equations? And B, how do we answer that question through the lens of another problem, that being the cycloid? Without further ado, let's get into the cycloid and into this video. Imagine a circle rolling along a flat surface. Focus on that white point on the edge of the circle. As the circle rolls, that white point traces this blue curve here, and that blue curve is actually a cycloid. It's just the path a point on the edge of the circle takes as the circle rolls. Our goal today is to integrate that curve and use this specific problem to find a more general pattern for integrating parametric equations. Let's get into it. To make today's problem easiest, I'll let the radius of our circle be 1. Instead of defining the cycloid using a function, I want to define it with parametric equations, specifically equations in terms of an angle theta. This is what our parameter theta actually looks like. It's the angle that our point makes with the vertical, and I want to use this angle to define coordinates for our red point on the edge of the circle. Now, that point is going to be in terms of x as a function of theta, and also y as a function of theta. This is how we're going to introduce this parameter and redefine our cycloid in terms of that angle. That red dot on the ground shows where our point started, and now I want to find out where is the center of our circle after we've rotated an angle theta. Well, using this equation, arc length equals radius times angle theta, with our radius being 1, we get that the arc length we've traveled is simply equal to the angle we've rotated. Now, the arc length is just the distance that we've traveled through space to get to where we are now. That's how far our center has traveled, and again, that is simply equal to our angle theta. If I draw this line here, though, we can see that the point on the edge of the circle isn't traveled all the way theta. No, it's instead theta minus this distance, which is sine of theta. And so the x-coordinate of our point is theta minus the sine of theta. So there you go, that's our x-coordinate in terms of theta. And now for our y-coordinate, well, we can see that this distance that I'm drawing now is simply the radius of our circle, which is 1. But our point is a bit above that. In fact, the distance it is from the center of the circle is this distance here, which is cosine of theta. Again, I'm referencing that right triangle I drew. And so we can see that the vertical height of our point is 1 minus the cosine of theta. And there we go. Now we've defined x and y in terms of theta. With our parametric equations out of the way, it's time to consider integrating. Now again, what I'm shading in now is the area I'm actually trying to find, but how do we generate that shape? Well, that's going to be when this circle rotates one full time. We're going to get one of these humps of our cycloid, and again, that's what we're interested in. Now, how does theta actually change? Well, if we're rotating one full time, we're doing one full rotation, theta is going to go from 0 to 2 pi. In radians, that is one full rotation around the circle. This is where we really get into parametric integration. Now, traditionally, if we want to consider an area, we would think of it as the integral of some function f of x dx. Now, if we had a function for our cycloid, that'd be good, but this is no good because there is no function, at least not a clean one or one that describes the entire cycloid, that we can reference here. Instead, we're going to have to rely on our parameter theta and translate this integral into that angle theta. Now, how do we actually speak the language of that angle? Well, it's important to consider that x is just a function of theta, right? And if we were to take the derivative of both sides, we again want to find dx, well, that's just going to be equal to x prime of theta d theta by the chain rule. Let's plug this back into our integral now. So the area we can rewrite as the integral from a to b. And now it's of f of x of theta. Remember, x is simply a function of theta, and then dx from above is x prime of theta times d theta. And there you go. Now our integral is speaking the language of theta. But I want to focus on this first term here, x of f of theta. This is the output, or the height, of our cycloid as a function of theta, and that's just the same as y of theta, is it not? It's a function that describes the height as theta changes. And so I'm going to do one last rewrite here of our integral and say that the area under this parametric equation, or any parametric equation for that matter, is y of theta times x prime of theta times d theta. And that is it. That is the form for all parametric integration and also this cycloid problem here. So let's apply this to this problem now and figure out the area underneath our cycloid. These are, again, our parametric equations for our cycloid, and we talked about earlier how theta is ranging from 0 to 2 pi. We're focused on one rotation of our circle. Again, I'm going to differentiate x prime of theta because we need that for our integral, and we can see that that's equal to 1 minus cosine of theta. Interestingly enough, for a cycloid, x prime of theta is equal to y of theta. So now if I go ahead and rewrite our integral down below, we'll see that a is equal to the integral from 0 to 2 pi, again that's where theta ranges from, of 1 minus cosine of theta, that's y of theta, times 1 minus cosine of theta again, that's x prime of theta, d theta. Let's go ahead and rewrite that integrand as 1 minus cosine theta squared. The next thing I'm going to do is expand that term. This is going to become 1 minus 2 cosine of theta plus cosine squared of theta. This new integral is quite simple. We have three terms being added together. Let's integrate each individually. So this 1 is going to integrate to theta, evaluated across our bounds. Minus 2 cosine theta is going to integrate to minus 2 sine of theta, evaluated across our bounds. And then I'm going to keep the cosine squared of theta term in the integral for now because I want to work with that a bit more separately. Before we work with cosine squared of theta, let's just evaluate these first two terms. Now this first term just simply evaluates to 2 pi. The second term here, sine of theta, evaluated from 0 to 2 pi. Well, sine of 2 pi is 0, and sine of 0 is also 0, which means this entire term is simply equal to 0. So we can erase that term there. And so a, the area under our cycloid, is just equal to 2 pi plus the integral from 0 to 2 pi of cosine squared of theta. How do we actually integrate cosine squared of theta? Well, a double angle identity for cosine is that cosine of 2 theta equals 2 cosine squared of theta minus 1. We can solve for cosine squared of theta in terms of cosine of 2 theta. If I go ahead and move this up, we can add 1 to the other side and then divide by 2. And from that we get that cosine squared of theta is equal to cosine of 2 theta plus 1, all divided by 2. Alright, awesome. This is our new integral. So a is going to be equal to 2 pi plus 1/2 of the integral of 1 plus cosine of 2 theta. Now the integral of 1 is simply theta, evaluated across our bounds from 0 to 2 pi. And then we have plus 1/2 of the remaining integral, which is just the integral from 0 to 2 pi of cosine of 2 theta d theta. Using inverse chain rule, this is simply equal to 1/2 of, and then cosine of 2 theta integrates to 1/2 of sine of 2 theta. Again, this is simply evaluated across our bounds, and all we have to do is plug in some numbers and we'll be left with our final answer. I'm going to bring out that 1/2 just to make it a little easier to see. If we plug in our top bound of 2 pi, we get sine of 4 pi, which is equal to 0. And if we plug in our bottom bound, we get sine of 0, which is also equal to 0. So this whole term here is actually just equal to 0. That means we can turn our attention to this first term here, this 1/2 of theta, evaluated from 0 to 2 pi. And when we go ahead and do that substitution, we get that this is simply equal to 1/2 of 2 pi. Now, 1/2 of 2 pi is of course just pi. And so, given that this whole final term is simply equal to 0, we're simply left with 2 pi plus pi. Now, of course, that is just going to be equal to 3 pi, and that is our final answer. Despite this video being oriented around the cycloid problem, the form of parametric integration that we discussed today is general and works for many examples beyond the cycloid. Thank you guys so much for watching. I hope you learned something new. If you have any questions, feel free to leave them down below. Without further ado, I've been the Natural Hogarithm, and have a great day.